Hey there, physical science students. This is Miss Ruark. We're in Unit 3 with energy, and this just so happens to be podcast 3.3 with energy. All right, so energy and work, how are they related? Well, all objects are going to have energy. Objects in motion will have energy, such as this lightning and this bicycle rider. An object at rest will have energy, such as this boulder here. Okay, and energy is just the ability to do work. Okay, so if work has units of joules and energy is work, well, energy should have units of joules as well, right? All right, well, there are different types of energy, and that's what we're going to talk about in this podcast. All right, first type of energy is potential energy, and you'll see that labeled as PE, okay? Not physical education, potential energy. And it is the energy of position, okay? So it's all about position. Actually, well, yeah, it's about position, and it's usually going to be when an object is at rest. So it's where it's sitting determines its potential energy. Okay, objects that are stretched or compressed, such as this rubber band here, or this spring, have elastic potential energy. And objects that are sitting high off the ground, such as this elevator, that was cute, roller coaster. Okay, the roller coaster high up off the ground on the top of that peak has gravitational potential energy because gravity will be pulling on it. All right, so gravitational potential energy. Let's talk about that. Gravitational potential energy, or GPE, depends on mass and height. Okay, let's come back to that. All right, so mass and height. Let's say that this apple here, this is an apple tree, and this apple here, hopefully you can see that. Let me make it a little bit bigger. Okay, so that apple and that apple, okay, they both have the same mass, but one of them is higher than the other one. So which one's going to have a higher potential energy? Well, the one on top is going to have a higher potential energy than the one on the bottom because the height of the object increases the potential energy. So if you increase the height for an object, you're going to increase the potential energy. All right, well, let's say, I need to erase some of this. Let's see. Let's erase that and that. Okay, let's say that we have this apple here. Okay, hopefully you can see it, and this apple here. They're both at the same height, but they're different masses. Let's say that this one here has a bigger mass, so let's say that it's 2 grams, which is not ideal because that's too small of a mass, but that's okay. And this one is 1 gram. Okay, they're both at the same height, but they have different masses. Which one's going to have greater potential energy? Well, the one with the bigger mass is going to have a greater gravitational potential energy because it's heavier. Okay. All right, gravitational potential energy, or GPE, or potential energy. The way you calculate that is you take the mass of the object times the free fall acceleration times height. Well, remember, free fall acceleration. Free fall is when the only thing acting upon it is gravity. So it's the acceleration due to gravity, which is 10 meters per second squared. Okay, so the mass of the object times gravity times the height of the object. Okay, so GPE, or potential energy, is equal to m times g times h. Okay, so let's do an example. We have a 65 kilogram rock climber which ascends a cliff. Okay, what is the climber's GPE, or gravitational potential energy, at a point 35 meters above the base of the cliff? All right, so we need to analyze this question first. What are we looking for? Well, we're looking for the climber's gravitational potential energy. So we're looking for potential energy. We know that this rock climber has a mass of 65 kilograms, and it ascends a cliff, which means it's going up in this direction. And we are 35 meters above the base of the cliff, which gives us our distance, or our height. Okay? Height. All right, so we know our equation here, GPE is equal to m times g times h. Well, m here is 65 kilograms, g is 10 meters per second squared, and h is 35 meters. So we plug that in, 65 times 10 times 35, and you should get 22,750. 22,750 kilograms times meters squared over second squared, or joules. And why joules? Because work is the same thing as energy. Work and energy both have units of joules, right? We work hard to get the joules. Okay. Kinetic energy is another type of energy that we need to look at. Okay, and this is the energy of motion. Kinetic energy is going to depend on the mass of the object. So here we have, it doesn't look like it, but these are ping pong balls. And here we have a bowling ball. Okay, ping pong ball and a bowling ball. If we roll those two, which one's going to have greater kinetic energy? Well, if you said the bowling ball, you're correct because it has more mass. Okay, also depends on the rate of acceleration. Okay, so let's say we had two ping pong balls here and we made one of them go at 10 meters per second squared and the other one we had move at 1 meter per second squared. Which one's going to have greater kinetic energy? The one with the greater rate of acceleration. All right, so kinetic energy is equal to 1/2 times the mass of the object times the speed of the object squared, or the velocity. Okay, so the equation would be 1/2 mv squared. Okay, depends on speed more than it does on mass. So the change in speed is going to have a greater influence on kinetic energy than the change in mass. Okay, because a small change in speed can give a large change in kinetic energy. Think about it. If you see a car wreck, okay, two car wrecks, same everything. The only thing that's different is how fast they were going. If there's one car that wrecks and it was going 10 miles per hour and another car that wrecks and it was going 85 miles per hour, which one's going to be worse? Well, if you said the one that has more speed, you're correct. Because there's more speed, it's going to give an even larger change in the energy of motion. All right, atoms have energy. So everything is made of atoms, and these atoms have energy. And these atoms, because they have energy, are in constant motion. Okay, it doesn't matter if it's a solid, liquid, or a gas. They have energy and they're in constant motion. If it's a gas, you probably have learned this already. They're bouncing all over the place, right? Boom, 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 boom. You love that. I know, it's great. All right, if it's a liquid, they're kind of flowing around each other. Right? And if it's a solid, well, you've got solid molecules and solid atoms, but guess what? They're not really moving. They're trying to, but they're bonded. So they're vibrating. They're just vibrating right here where they're sitting. They're in constant motion. All right, well, temperature is how we would determine, one way that we could determine how much energy they have, because temperature isn't really a measurement of heat. Temperature is a measure of kinetic energy. Okay, so let's do a kinetic energy problem. All right, well, what is the kinetic energy of a 44 kilogram cheetah running at 31 meters per second? All right, so we're looking for kinetic energy, so we're going to circle that. Okay, we have 44 kilogram cheetah, so that's the mass, and it's running at 31 meters per second, so that's the velocity. All right, well, our equation for kinetic energy, 1/2 mv squared. We have our mass, we have our volume, we have our velocity. All we have to do is the mass. So we're going to plug that into the equation. 1/2 times 44 times 31 squared. Now remember, this squared goes to everything. So you have to square the seconds, you have to square the meters, and you have to square the number. Okay? And you should end up getting 21,142 joules. Remember, joules because it's energy. All right, other forms of energy that we would need to know. Mechanical energy. Mechanical energy is the sum of potential and kinetic energy. So potential and kinetic energy added together, you get mechanical energy. Okay, so here's the potential energy because it's what's stored inside this object. It has a lot of potential energy because it's up higher. Okay, the kinetic energy, the potential energy changes into kinetic energy as it moves. And mechanical energy is all of it. It's when it hits it and drives the nail through the piece of wood. All right, non-mechanical energy is the energy that comes from molecules. So if you were to eat a banana and you are to break down those molecules inside that banana, the carbohydrates and the sugars, and you get energy from them, that would be non-mechanical energy. All right, if a chemical reaction occurs, such as this piece of dynamite blowing up, okay, that's involving potential energy, and we say that it is chemical energy because there's energy happening on the chemical level. All right, and then energy from the sun. Okay, again, another form of chemical energy. You could also say it's thermal energy because it's heat that you get from it as well. Light energy because you get the light from the sun, and you get photosynthesis. And energy from appliances, the things that you have in your house, we call that electrical energy. All right, energy, you've probably heard this before. Let's become familiar with it again. Energy cannot be created or destroyed. It changes forms. Okay, so that's the law of conservation of energy. Very important that you know that. Okay, so here we have a cannon that's shooting off this cannon. It looks more like a bullet, but it's shooting off this, let's just say it's a rocket. Okay, chemical energy is what helps to fire off the rocket. The chemical energy is changed into kinetic energy. It also has a little bit of potential energy as well in it because it is moving, but it's still got some stored. Okay, as it comes up this way here, it's going to have where it kind of stops going, you know, propelling itself, so it has more potential energy, less kinetic, but there's still the both there. Okay, mechanical energy, and then we're coming back down this way. When it gets down here, it causes a big explosion, and it changes into heat, which is energy, right? Kinetic energy of molecules. Okay, so it's not going to change or be destroyed or created. It's just going to change form as it goes through its phases. All right, last thing we need to talk about is efficiency. So efficiency of a machine. When you use a machine, only a portion of work that is done is useful work. And the reason why only a portion of it's done and not all of it is because there's friction. Everything has friction. Well, unfortunately, friction gives off energy, and that energy can be felt as heat. Okay? Here's a match. When you light that match, when you strike it here on the ground, that's causing friction, which is heat, and that's what helps to light that match up and fire. All right, so to tell how efficient a machine is, you're going to do a ratio of useful work output over work input. So let's try an example. All right, a sailor uses a rope and an old squeaky pulley to raise a sail that weighs 140 newtons. He finds he must do 180 grams of work on the rope to raise the sail by 1 meter, and he does 140 joules of work on the sail. What is the efficiency of the pulley? And it says to express your answer as a percent. All right, well, let's analyze this. We know that we need to find the efficiency of the pulley. Okay, so we're looking for the efficiency. We know that this sail has a force that's equal to 140 newtons because weight is force. All right. This is the amount of work that he needs to do. Okay, so that's a type of work. And this is the amount of work that he does do. So that's another type of work. Okay, so the question is efficiency. Oh, and I forgot this one. I'm sorry. I forgot this one. This would be distance, right? And we're going to raise it, so that's going to give us our direction. We got to label everything, whether we use it or not. All right, to find out the efficiency of the pulley, we need to do useful work output over input. Okay, so the output is what you get from it, and the input is what you put into it. So 140 joules, this is how much they got out of it because it was actually done. Okay, what is actually done. And then input, this is what it needs. It would help if I could spell what it needs. Okay, so 140 joules is what was actually done over what it needs, which is 180. And we divide those and we get 0.78. Well, to change to a percentage, well, how do we do that? Do you know? Multiply it by 100, right? Yeah, so if we multiply this by 100, we end up getting our percentage. And that's how we got that. Multiply it by 100. Okay? All right, so I think that's it. Here you go. Something to leave you with. I'll see you in class.